Hello everyone. In this macro video, I will solve some problems regarding the drawing boat plot. Uh, in the first question, we would like to show that the boat plot for the transfer function hs equal to 1 over s is the form shown in the figures. In order to draw the boat plot for the transfer function, we need to follow these steps. The first step is to substitute s as the j omega in the transfer function. The second step is to find the real and imaginary components of the transfer function after substituting s equal to j omega. The third step is to calculate the magnitude of the transfer function using a equal to root square of re square plus real part square plus imaginary part square. And the fourth step is to calculate the phase angle using where the phase angle is tangent inverse of imaginary part over real part. For this specific case, so the first step is that to substitute j omega in transfer function. Instead of the s, we have the j omega here. The next step is to find the real and imaginary components. In order to find the real and imaginary components, I multiply the transfer function to j omega by over j omega in order to get rid of the j in denominator. You need to keep in your mind, in order to find the real and imaginary part, we need to get rid of the imaginary part in denominator. We need to have just imaginary part in numerator. So after doing this multiplication, I will get hj omega equal to minus j omega over omega squared. After cancelling out omega, I will have hj omega equal to minus 1 over omega j. So this is the transfer function of hj omega. So based on this relation, I know that the imaginary part of this transfer function is minus 1 over omega j, and the real part is 0. So if I want to calculate the amplitude or magnitude of the transfer function, I will need to use the a equal to real square plus imaginary square. By substituting these values of the real and imaginary, I will have this function, so which will be equal to 1 over omega. So the amplitude is equal to 1 over omega. Similarly, in order to plot this amplitude phase in the logarithm phase plate, I need to use the 20 log of a. So 20 log of a will be 20 log of 1 over omega. We know that the logarithm of alpha over beta is equal to log of alpha minus log of beta. So by using this rule, I know that the 20 log of 1 over omega will be equal to 20 log of 1 minus 20 log of omega, and as we know, 20 log of 1 is 0, so it will be equal to 0 minus 20 log omega. And finally, 20 log a of this transfer function will be equal to minus 20 log omega. Similarly, if I want to calculate the phase angle or phase shift of this transfer function, I have phi equal to tangent inverse of imaginary part over real part. By substituting the values for the imaginary part and real one, I have the tangent inverse of minus 1 over omega over 0. As we know that minus 1 over omega over 0 is minus infinity. So tangent inverse of minus infinity is minus pi over 2. If you look at the, so I need to plot this function in the logarithm phase and logarithm plot, and this angle in the logarithm plot. Here I know that the amplitude is equal to minus 20 log omega. If I put omega equal to 1, I have minus 20 log omega equal to 0, which means at omega equal to 0, amplitude is 0. And I have minus 20 log minus 20, which means that I have the minus 20 decibel per decade. It's worth to define the definition of a decade. An interval of two frequencies with a ratio equal to 10 is called a decade. so that the range of frequencies from omega 1 to omega 2, where omega 2 is 10 omega 1, is called a decade. So if I want to plot the phase plot, as you see, at omega equal to 1, amplitude is 0. After that, or before that, I need to plot a straight line with the slope of -20 in decade. As you see, for example, from 0.1 to 1, I have 1 decade, and from here to here, the slope is -20. Starting from 20, it goes to 0, and if you look at this frequency range from 1 to 10, I come from 0 to -20, so the slope is -20, and magnitude at omega equal to 1 is 1. Similarly, if you want to plot the phase of this transfer function in terms of the frequency, since phase is constant and it is equal to -pi/2, it is a straight line with the slope of 0. For in fact, or in other words, the angle is always -90 regardless of the value of frequency. Okay, in the second problem, I would like to find draw the both plot of this transfer function. To find this one, I have gs equal to 10 over 10 s squared plus 110 s plus 100. At the first step, I just factor out 10 from denominator and denominator, so I will have 1 over s squared plus 11s plus 10. If I find the roots of this denominator, I will find that I have two simple poles, one equal to -1 and another one equal to -10. In order to plot this transfer function, before that I need to make sure that all poles or zeros are in the standard format. We know that the standard format of a pole in transfer function is in form of the 1 over tau s plus 1. Here tau for the first component, tau is 1, but for the second one, tau is 0.1. So the actual transfer function is 0.1 over s plus 1, 0.1 s plus 1. In order to plot in order to draw the both plot of this transfer function, I need to separate each component of this transfer function and plot the the both plot of each component, and at the end add up the all plots of the transfer functions. Here I have three components, one constant gain which is equal to 0.1. I have pole 1 equal to 1 over s plus 1, and pole 2 equal to 1 over 0.1 s plus 1. So what I need to do is I need to plot the both plot, or to draw the both plot for these three components separately. I start from k constant gain, k equal to 0.1. For the constant gain, again we need to follow the steps I discussed already. For the k equal to 0.1, the real time is 0.1, imaginary part is 0. So if I calculate, the amplitude is 0.1, which is constant. So 20 log of a in this case will be -20. In other words, the 20 log of 0.1 will be -20. And angle will be tangent inverse of 0 over 0.1, which would be 0, tangent inverse. So for the second one, let me give you instruction how to draw a both plot for a general simple pole. Assume I have a general form of the transfer function of 1 over tau s plus 1. In this case, first I need to substitute s equal to j omega. By substituting s equal to j omega, I have this ratio. The second step is to find the real and imaginary part. To find the real and imaginary part, I need to get rid of j in this denominator. To do so, I multiply the numerator and denominator by complex conjugate of this complex number. So to do so, I have the 1 over tau j omega plus 1 multiplied to minus tau j omega plus 1 over minus tau j plus omega plus 1. So this value is the complex conjugate of this complex number. By doing this multiplication, I will have minus tau j omega plus 1 over tau j omega squared plus 1 squared. If I do this multiplication, I will have minus tau j omega plus 1 over tau omega squared plus 1. So it will be equal, so if we look at this transfer function, this ratio, the real part is 1 over tau omega squared plus 1, and the imaginary part is equal to minus tau omega over tau omega squared plus 1 j. So the real part is 1 over tau omega squared plus 1, and imaginary part is minus tau omega over tau omega squared plus 1. To calculate the amplitude, A will be equal to the real part squared plus imaginary part squared. After doing the some maths, I will find out that A will be equal to roots 1 over roots of tau omega squared plus 1. If I take the 20, and I know that the log of the roots alpha is equal to 1 over 2 log alpha. Using this rule, I see that the 20 log of A will be minus 20 log roots tau omega squared plus 1, and which is equal to minus 10 logarithm tau omega squared plus 1 according to this rule given here. So in order to plot this function in the logarithm plane, I need to do some assumption. At the first, assume tau omega is much less than 1. Actually, this function is too complicated and nonlinear, and we need to make some assumption to simplify this function. To do so, I first assume that tau omega is much less than 1. In other words, omega is much less than 1 over tau. If tau omega is much less than 1, we can ignore this component compared to 1, because 1 is much bigger than this value. So by this assumption, I will have 20 log of A equal to minus 10 log 1, because this tau omega is very small value, has a very small value compared to 1. So I can ignore this one. Compared to 1, I will have minus 10 log 1, and since log 1 is 0, which means 20 log A is equal to 0. This means that for the omega, which are much less than 1 over tau, the amplitude would be 0. In another case, if tau omega is much bigger than 0, if you again compare these two components, tau omega is much bigger than 1, we can ignore 1 compared to the value of the tau omega squared. So if we assume tau omega is much bigger than 1, which means omega is much bigger than 1 over tau, 20 log of A will be equal to minus 10 log tau omega squared. Since we have the square here, it will be equal to minus 20 log tau omega. Similar, so, here it's worth to mention that omega equal to 1 over tau is known as corner or break frequency of the transfer function. For the phase, in order to draw the phase of this function of a simple pulse, I have the tangent inverse of imaginary part over real part, which is tangent inverse of minus tau omega over tau omega squared plus 1 over 1 over tau omega squared plus 1, which means these two cancel out each other, which means tau phi will be equal to tangent inverse of minus tau omega. In this case, we assume if tau omega is much less than 0.1, or omega is much less than 0.1 over tau, phi will be 0, which means tau omega is very small value and near to 0, almost 0, so tangent inverse of 0 will be 0. If tau omega is much bigger than 10, it means omega is much bigger than 10 over tau, so the tangent in this one will be a huge value, a minus huge value, which means tangent inverse of infinity, almost infinity, will be minus pi over 2. in a special case, when the tau omega is equal to 1, which means omega equal to 1 over tau at the corner frequency, phi will be minus pi over 4. So we consider three regions for the omega, when omega is much less than 0.1 over tau, when omega is much bigger than 10 over tau, and when omega is 1 over tau. In fact, we consider one decade before corner frequency and one decade after corner frequency in order to see how the phase will change in terms of omega. So by considering this one, let's start over. We have a constant gain k equal to 0.1, so the 20 log of a is equal to minus 20, and I have the pole p1 as a 1 over s plus 1, tau is 1, which means the corner frequency for this pole is 1. So in order to plot the amplitude, first I assume omega is much less than 1, which means for the this omega's 20 log a is equal to 0. For the omega much bigger than 1, I have 20 log a, which is minus 20 log omega. For the second pole or P2, transfer function P2, I have 1 over 0.1 s plus 1. In this case, omega C2 or corner frequency, second corner frequency is equal to 10. When omega is much less than 10, I have 20 log a equal to 0. When omega is much bigger than 10, I have 20 log a equal to minus 20 log omega. So if I want to plot this one, first I plot the both plot of constant gain, which is minus 20. It is constant regardless of the frequency. For the second one, I have the corner frequency at the 1. Before this corner frequency, the amplitude is 0. After this corner frequency, I have a straight line with the slope of minus 20. If you see here, from the frequency 1 to 10, the slope changes minus 20. So the line is the straight line has the slope of minus 20. For the omega C2, the corner frequency is at omega equal to 10. Before that, the magnitude is 0. After that, I have the straight line with a slope of minus 20 again. As you see here, from 10 to 100, the difference in the magnitude is minus 20, which means I have a straight line with the slope of minus 20. At the end step, I just need to add up this these both plots all together to find the magnitude plot of the overall transfer function. To do so, first let's look at the omegas less than omega c1, which is 1. In this case, the first and the magnitude, I have just a constant magnitude minus 20, so I need to add up these magnitudes together. I will have the minus 20. After omega c1, I have the magnitude of minus 20, and I have the slope, a straight line with the slope of minus 20. So if I add up this one and this, the purple line and the green line, I will have a line starting at minus 20 with the slope of minus 20 decibel per decade. And after omega c2, I have the magnitude of minus 20, and I have two lines with the slope of minus 20. I need to add this line to this line. If I add this line to this line, I will have a straight line with the slope of minus 40. So if within one decade, or minus 40 decibel per decade, if you see from 10 to 100, which is one decade, the slope of the line is minus 40. So the orange line shows the transfer function, the asymptotics of the transfer function of the overall transfer function. In order to plot the phase angle of the or phase shift of the transfer function, we follow the same similar approach for the magnitude one. So for the k equal to 0.1, the magnitude is, the phase shift is 0. When p1 is equal to 1 over s plus 1, which means the corner frequency is 1. If omega is much less than 0.1, which is the 0.1 over 1, phi will be 0. If omega is equal to 1, phi will be equal to minus 45. If omega is much bigger than 10, phi will be minus 90. Similarly, for the P2 equal to 1 over 0.1 s plus 1, omega C2 is equal to 10. In this case, is omega is much less than 1. 1 is in fact 0.1 over tau, which tau is 0.1, which will be 1. So phi will be 0. If omega is equal to 10, which is the corner frequency, phi will be minus 45. If omega is much bigger than 100, phi will be equal to minus 90. So again, if I want to plot this asymptotes on the logarithm plane, for the k equal to 0.1, the phase angle will be always 0. I have the corner frequency omega c1. At the omega c1, the angle is minus 45. Before that, before 1 decade before, which is 0.1, the magnitude is the shift angle is 0. For the 1 decade after that, shift angle will be minus 90. And if I connect these two lines together, I will find the phase angle for the phase angle plot for the first port. For the second port, I have the corner frequency at 10 with the phase angle of minus 45. 1 decade before, which means at omega equal to 1, the angle is 0. After and 1 decade after, I have the phase angle of minus 90. Before that, I need just to connect these two lines together, crossing omega c2. So similarly to the magnitude plot, I need to just add up these plots together, or asymptotes together. Before the omega 0.1, all angles are 0, so I have the 0 angle. After 0.1, I have just up to frequency 1, I have just one straight line, one angle. So excuse me, before after 100, I have two angles with two minus 90 angles, so the summation will be minus 180. So the only thing that I need to do is to add these two lines together. So this will be the overall phase plot of the transfer function. Here is the actual both plot of the transfer function. As you see here, for the magnitude one, before omega c equal to 1, I have the amplitude of the minus 20, and after the magnitude of the, before that, I have the line almost with the straight line almost with the slope of minus 20, and after 10 I have the straight line with the slope of minus 40. And the same for this phase angle. Before the frequency 0.1, I have the almost 0 angle, and for the frequencies after 100, I have minus 180, and after that I have just almost a straight line. But here is the very actual line, and in your exam you just need to plot the asymptotes and a very rough estimation of the both plots, both in magnitude and phase angle. I hope you find this video useful for your final exam, and if you have any further question, please feel free come to my office or post a comment on the comment section of the video, and I will answer your questions. Wish you all the best and have a good day.